Hello everyone, I am Iman Hamid Muhammad Ahmed in grade 10 advanced from Al Badia School. Today I am going to activate an experiment from Lobster for my stream project. It is about the law of universal gravitational. Today we will use the gravity to orbit the moon. Come on, let's go! At the end of this experiment, I will be able to understand the difference between weight and mass, measure the gravitational acceleration near the Earth's surface, describe the circular orbits, and describe the distance dependence of g. First thing, I must wear the lab coat to obtain my safety in the lab. Next, I'm going to introduce a famous scientist, Isaac Newton. He described the difference between the mass and the weight. The mass of an object is the amount of matter it contains, but the weight of an object is a measure of the force exerted on the object by the gravity. Which law connects the acceleration of an object to the force acting on it? It is Newton's second law of motion, which states that the acceleration of an object is equal to net force divided by the mass, or the force equals to the mass times the acceleration. Newton describes the attraction force between objects. The law of universal gravitation states that every object with mass is attracting every other object with mass in the universe. Now, let's see how we can measure the gravitational acceleration with a pendulum. All we need to know is the length of the thread and the period of one oscillation. Hang the clamp on the stand and put the pendulum thread as shown above. Choose the mass with 200 grams and then run the pendulum for 5 seconds in 3 oscillations. As you can see, the result G was 9.8 meters per second squared, and this is the gravitational acceleration near the surface. What would be the outcome of the experiment if we doubled the mass attached to the pendulum? I can say that the gravitational acceleration would be unchanged because all objects on Earth fall at the same constant rate. Now, I will investigate how the gravitational acceleration is dependent on m and the distance between the masses. Let's start with the dependence of gravitational acceleration on m. M is the mass of the Earth in our setup. The mass of the Earth is 5.97 times 10 to the power of 24. As the previous experiment, I will run the pendulum for 5 seconds in 3 oscillations, and the result G is 9.8 meters per second squared. Have a look at the data point on the screen. How are G and M are related? The answer is G directly proportional to M. Thus, according to Newton's second law of motion, the gravitational force must be proportional to both masses, the mass of the object and the mass of the Earth. Next, let's see how Newton thought about the motion of satellites. Imagine a cannonball on the top of a high mountain, firing the cannonball horizontally with a given horizontal speed. The cannonball is a projectile, and its motion has both vertical and horizontal components. Like all projectiles on Earth, it would follow a parabolic trajectory and fall back to the ground. If the cannonball's horizontal speed were increased, it would travel further across the surface of Earth and still fall back to the ground. If an extremely powerful cannon were used, however, the cannonball would travel all the way around the Earth and keep going. It would fall toward the Earth at the same rate that the Earth's surface curves away. In other words, the curvature of the projectile would continue to just match the curvature of Earth, so that the cannonball would never get any closer to or further away from the Earth's surface. The cannonball would therefore be in orbit. Which of the following statements is correct? An object orbiting the Earth is in constant free fall but never hits the Earth. For example, the Moon. In general, what is the name of the force that makes a body to follow a curved path? It is the centripetal force. We can calculate the gravitational acceleration at different distance from the center of the Earth. For an orbiting object, we know that the gravitational acceleration is equal to the centripetal acceleration. With some basic operations, we see that all we need is the distance and the orbital period to calculate the gravitational acceleration. This is exactly what Newton did back in the day. The period of the pendulum is equal to 2 pi times the square root of the length divided by the g. We can rearrange this formula so that the gravitational acceleration is equal to 4 pi squared times the distance divided by the period squared. What is your guess for the distance dependence of g? G depends on the reciprocal of the squared distance. This is an example of the inverse square law. Newton concluded that the gravitational force between two objects is equal to the constant g times the masses divided by the squared r, where g is the gravitational constant and r is the distance between the two objects. What is the gravitational force between Newton and the apple? Using the law of gravitational force and substituting the values, the result gravitational force is 5.2 times 10 to the power of negative 10.
أَمَّنْ جَعَلَ الْأَرْضَ قَرَارًا وَجَعَلَ خِلَالَهَا أَنْهَارًا وَجَعَلَ لَهَا رَوَاسِيَ وَجَعَلَ بَيْنَ الْبَحْرَيْنِ حَاجِزًا أَإِلَٰهٌ مَّعَ اللَّهِ أَإِلَٰهٌ مَّعَ اللَّهِ بَلْ أَكْثَرُهُمْ لَا يَعْلَمُونَ.
Congratulations! If your result in this experiment is 100, then now you will be able to teach the law of universal gravitational to your classmate. Thank you for watching and hope you enjoy.